Okay, thank you, Datta. So, good morning, all of you. Today, we are going to talk about the another thermal energy based non-convection machining process, that is electron beam machining. Okay, so last three lectures we have gone for the laser beam machining. Okay, today we'll start the electron beam machining. Okay, now I will share my screen. Whether screen is visible, the Sharath, Rohan, please reply anyone.
Yes, sir. Yes, sir.
Whether my screen is visible. Okay, thank you. So today we are going to discuss on electron beam machining. In this electron beam machining, actually there is a bombardment of high velocity stream of electrons on the your workpiece surface. So this whatever the electron bombardments are there no, on the your workpiece surface with a high velocity, that velocity around 60% of the velocity of sunlight. So because of this bombardment of the your electrons on workpiece surface, the material like what are the material of your workpiece. So that materials into the small area on your workpiece surface, it get melts and then it vaporizes. And when that melting will occur, that means the temperature rises to a very high temperature. Okay, so the material on your workpiece material it get melts and vaporized, and due to that machining is going on. Okay, so simple is there of this electron busting, okay, process. Okay, once again I will repeat here, the bombardment of high velocity stream of electrons, okay, will be occurred. That bombardment of velocity, that high velocity stream of electron on your workpiece will occur, and due to that bombardment, uh, on which surface or on which portion of the workpiece that bombardment occur, no? So on that portion of that portion, temperature will rise, okay, up to the high temperature, and due to that the melting and vaporization will occur, and through that a removal of the metal will take place. Okay, so this process actually it is used for machining thousands of hole on a thin sheet, okay, which is used in aerospace industry, food processing industry, then cloth industries, and very high aspect ratio for making of a very high aspect ratio holes. Thousands of holes you can consider on your workpiece surface, irrespective of the metal property like metallic property, uh, m- metallurgical property, mechanical properties of your workpiece. You can perform the uh, machining operation using this electron beam machining. Okay, so this material, okay, yeah, for this process, whatever your workpiece material is there, no, it may be electrical conductive or electrical non-conductive, or maybe ceramic, metals, or any kind of metal, any kind of ceramic uh, on that material, this process it was. Okay, so here actually in this process there is a filament, okay, which is heated with a very high temperature. So because of this heating of that filament, so electrons emits, okay, from that cathode, and that from the cathode means that cathode filament, or that filament may be heated from the your radiation from another body, okay, from the on a that uh, solid block of your cathode, okay, and that on that solid block of filament, also it can be generated by your electrons. Okay, so these electrons it emits from the your cathode, then the cathode filament, and it passes through a magnetic lens to coincident or to concentrate or to reduce the diameter of that electron beam, and it goes further and it bombards on your workpiece. Okay, so that is the fundamental. Now we'll discuss the remaining. Okay, so actually, electron beam machining process uh, having two types of methods are there. Okay, one is the thermal type, and another one is the non-thermal type. So in the normal, that in non-thermal uh, type of this electron beam machining, in this type of non-thermal type, electron beams are used for generating a chemical reaction. Okay, so for generating the chemical reaction, the electron beams are used. Okay, so this non-thermal uh, type. Okay, we are not going to study or we are not going to discuss here. Okay, we are going to discuss only thermal type of electron beam machining process. Okay, uh, in this thermal type. Okay, in this thermal type. Okay, here cathode is used. Okay, and that cathode is heated to that filament. Okay, that is heated to a very high temperature. So this uh, large or that stream of large number of electrons comes as a small diameter beam, that is electron beam through that your filament. Okay, you can see the stream of that cathode filament is heated, then stream of a large number of electrons as a small diameter beam is uh, comes from that. Okay, so that uh, stream of large number of electrons it emits from the your cathode, from a heated cathode, and it comes out a small diameter beam. Okay, so it moves toward the your workpiece with a very high velocity, and it bombards on your workpiece surface. So machining is going on due to that bombardment of these electrons on your very small localized area of your workpiece. So as it bombarded that electrons, as it bombarded on a very small localized area, that time huge amount of temperature is generated on your portion of your workpiece surface. So machining is going on due to the that uh, high generation or high temperature generation. That means the due to the melting and the vaporization of this workpiece material. Okay, from your material which is from your workpiece surface, it gets melted and vaporization will start from that localized area. Okay, that is the working principle of the this electron beam machining. With the help of the diagram, I'm going to discuss that. Okay, next that I'm going to show the diagram of the electron beam machining. Okay, so here I have the written that steps, uh, working principle steps of the electron beam machining. Okay, you can see cathode filament is heated, then a stream of large number of electrons as a small diameter beam will be generated from that cathode filament, and then that stream of high velocity electrons it moves towards your workpiece, and due to the bombardment of electrons in that localized area of your workpiece surface, their temperature will rise. Okay, very high temperature will be generated on the workpiece surface. So machining is going on due to the melting and vaporization of this material from your workpiece surface from your very localized area of your workpiece. Okay. So whatever the working principle of EDM or LBM or this EBM, okay, all working principle, all these three are the same. Okay. So So this kinetic energy of this electron beam, no, that is used for machining to takes place, and which convert this out of the kinetic energy of your electrons are there, electron beams are there, no, actually which converts this kinetic energy of beam into that electron that electron beam, high velocity electron beam, that kinetic energy convert into the heat energy. Okay, so it can produce the holes of different shapes. Okay, as I have mentioned earlier, that you can generate the thousands of holes using this electron beam machine. So any kinds of the holes other than circular also can be generated by deflecting this electron beam at a certain angle. Okay, at a certain angle. So workpiece material can be, as I have mentioned, that it can be conductive, electrical conductive or non-conductive. Any kind of workpiece can be machined irrespective of their hardness, mechanical and metallurgical properties. That material can be machined by this process. Okay. Also, another thing is that in this process or for this process, okay, please remember this point. For electron beam machining process, vacuum is required. Now, why vacuum is required? It's the answer I'm going to give in the next slide. So, this in this process, you can see here I will show the schematic diagram of electron beam machining. So, this machining chamber for the electron beam machining system, the machining chamber should be vacuum chamber because uh, this electron beam when it travel so far air is there into the for example if in machine chamber if air is there into the chamber, so it will collide on that you what is your electron beam are there, bro, so it will collide on the your air molecule. So it's a strength, that electron beam strength will be able to, so that is why this vacuum is generated into your machining chamber. Also, this cathode, it is used as a tungsten cathode. It is used as tungsten cathode is used. Okay, you can see the here cathode grid here. You can see cathode grid. Okay. Cathode in this schematic diagram of electron beam machine, you can see the cathode grid is there. That is the filament. You can see filament is there. Okay, through that we will get the high velocity electrons. Okay, high velocity electrons, and then you can see we can get the stream of electrons. Okay, and here we have the this submerging chamber, and there in that submerging chamber, vacuum is there. Okay, so machining will occur in vacuum. Okay, for the in this electron beam machining. So remember this point. Okay, in exam, MCQ based exam will be there. No? So that time definitely this question will be there. Okay, so remember in non-conventional machining, only one process is there in which vacuum that machining chamber is or that machining will occur in the vacuum. That is the electron beam machining. Please remember. So the machining chamber should be vacuum chamber. Okay, that vacuum should be there in that your machine chamber. So due to that only vacuum chamber it is called. Okay, in this diagram also. And that what are the cathode is there also that is used that cathode means your tungsten cathode is used. Okay, and again if air is there in the your machine chamber, so it will immediately it will be oxide. Okay, it will be oxidized. Okay, so to reduce or to avoid this oxidation of this tungsten filament cathode. So this vacuum chamber is used. Okay, to avoid the that collision of electron beam on your air molecule. Due to that, it will reduce the strength of the electron. And the second is the to avoid the oxidation in that machining chamber, oxidation of this tungsten filament cathode. Okay, so vacuum chamber is used. Okay, so your beam size, okay, this diameter of the beam size should be less than your diameter of hole to be produced. Please remember the diameter of the uh, beam size, okay, or diameter of your electron beam, that should be the less of your desired hole size. Okay, so that point you should remember. Okay, okay. So what are the ejection of the molten material. Okay, that how this molten material is ejected, or that molten or the vaporized material is ejected from the workpiece surface. That question is okay, because after that machining, the molten material that the vaporized material will be there on your workpiece surface. Okay, so how to inject or how to take away from the that machining or vacuum chamber, that question will arise. So at the what are your that, or we can call at the back side of the your workpiece, uh, there is a backing material is used. Backside of your workpiece, backing material is used. So after machining on the top surface of the workpiece, so when it reaches to the your bottom side of your workpiece, it also vaporizes that vaporize the your backing material. So this backing material also vaporize, so it comes out as a high pressure. It comes out as a high pressure. So this backing material, it comes out as a very high pressure. So while coming as a high pressure, it also ejects the your molten or your vaporized material. Okay, on your workpiece surface. Okay, so when your backing material will vaporize, that time it creates the high pressure, and when that high pressure going to expel or yeah, taking away from the your chamber, no? So that time it ejects the molten or vaporized material on your workpiece surface. So it expels the your molten or vaporized material from the your workpiece surface. So at the back side of your workpiece surface, there is a backing material is used. Please remember. So that is why the backing material is used. Okay, because backing, why to use the backing material in this electron machining? If that question was asked, this that time you should give the answer. Okay, uh, so again that as I have mentioned that non-circular holes also can be generated by this electron beam machining process. Non-circular holes can be generated in this by using this electron beam machining. Any kind of shape, any kind of shape of the workpiece on the your workpiece can be generated by this electron beam machining. So you can you can keep your beams, okay, fixed beam, and you can travel the you can move your workpiece on your computer numerical CNC table also. Okay, so that you will get the any kind of shape. You can place your workpiece on your CNC table, and you can generate any kind of complex shape, or you can move your beam also on your workpiece surface using your CNC table. Okay, so in both way, you can generate any kind of non-circular holes on your workpiece surface. Please remember this point. Okay, so circular big holes can be generated. You can move your beam along the perimeter of the circle, so you can generate the bigger size holes also by using this uh, EBM process. By using EBM process. Okay. Now come to this schematic diagram of electron beam machining setup or the system. Okay. Now before discussing, I request if you please draw this diagram. Okay. Because this is the only diagram through which you read the working principle or the all the components of this room. Now I will give you 2 minutes to draw this diagram. Okay, please hurry up. Electron beam machining system setup diagram or the schematic diagram. Okay, okay, simultaneously you can listen to me. So actually, this slide it contains one figure. Okay, and this is a schematic diagram of electron beam machining process. You can see here. This is a cathode. This is a cathode. You can see the name is also given. So you can see here. This is a cathode here. So this cathode filament it is actually heated up by using the high voltage lead. Okay, high voltage lead. Now the small question arises that how to produce the electron. Now to generate the electron, here we are going to use the tungsten filament cathode. Correct. Now to heat that tungsten filament, here we have used a high voltage lead. High voltage lead. You can see this high voltage lead. Okay, high voltage lead, and there you can see. So using this high voltage lead, this cathode filament, it is actually heated up. So this electron beam or the stream of electrons are coming outside from your cathode filament, which is made up of the tungsten. Because of the repulsion from that, how electrons will produce, because of repulsion force from your cathode. Okay, so electrons are actually negatively charged. Okay, or here this cathode also they are negatively actually it is connected to the negative terminal of the power supply. Okay, negative terminal of the power supply. Correct. So due to that, your electrons are the negatively charged. Okay, so these electrons are expelled with a very high velocity, and it is coming towards this anode. You can see this anode. It is coming towards the anode. Okay, so it is attracted towards the anode here. So actually, this is the anode. Correct. So as it attracted towards the anode, it is also expelled. What are the? It is expelled by the cathode. So it generated high velocity, very high velocity. It is generated. Okay, that means electron beam. It contains the very high velocity. So it is the that velocity. It is around 66% of the velocity of the light. Okay, velocity of the light. 66% of percent of velocity of light. Okay, so it is that high velocity generated electron. It is passed through this wall coil. Okay, you can see here wall coil is used. So this whatever the stray electrons are there, no. Okay, what are the stray electrons are there, no, that are filtered. Actually, it is actually filtered, and that stray electrons are filtered through this wall. Okay, so that is function of the wall, and you can see this what happening inside this vacuum chamber. So you can see using this. You can see. Okay, actually this is a total chamber. Okay, which is filled with the vacuum. So we can call this vacuum chamber. Now, what is going to happen, or what is happening in that machining chamber or vacuum chamber? If you want to see for that purpose here, optical viewing or optical view system is provided. Okay. Now, this electron beams is passing through this magnetic lens. You can see here magnetic lens are used. Okay. Here magnetic lens are used. Okay. So your electrons beams are going to through this magnetic lens. This is a magnetic lens. And the working principle of this magnetic lens is that so it actually concentrates all the beams into the a certain point. Okay, that means all the what are the scattered electrons beams are there, no, that will be concentrated using this magnetic lens. That is the uh, that function of this magnetic lens. Okay, magnetic lens is actually it concentrates all the beam into the certain point. So it reduces the diameter of that electron beam by passing through the okay sorry actually to pass that electron beam toward the your workpiece. So that your magnetic lens it concentrates your electron beam into the smaller diameter beam. You can see into the smaller diameter. Okay. So after that, it passes through the after passing magnet lens that electron beam, and after that, it passes through the deflection coil. It passes through the deflection coil. You can see, and after doing after passing through the coil, falls on your workpiece surface. On it falls on the workpiece surface. Okay, into the very small area, and that very small area means the your localized area. Correct. So when it falls on the workpiece surface into the very small area, into the localized area. So because of this, okay, falling or the striking or impingement, or you can call the because of this bombardment of high velocity electron beam, it melts and vaporizes the material from your workpiece, and the backside of your workpiece, at the backside of your workpiece, uh, that chemical backing material is used. Okay, chemical backing material is used. So when these holes actually extended, actually what are the holes you want to generate, or holes which one you want to produce on your workpiece. So when that holes is actually that extended toward the end of your workpiece, no, so that time this backing material also because of the heating of that high velocity, high temperature of the your electron beam. So because of that heating, that this high velocity gases are that chemical backing material. So from that high velocity gases are generated. So this gas, when it coming outside, okay, from your chamber, no, with that coming out of the chamber, so with a very high pressure, that time it expel whatever the molten material or vaporized material is there, no, so that is going to expel along with the high pressure of your gas. Okay, now you got the point. Okay, of why to use the backing, the chemical backing material at the backside of the your workplace. Okay, and how the that vaporization, that how gas is going to generate of your backing material due to the heating, and with a very high velocity, high pressure of your gas, how it is going to expel the your molten material or vaporized material of your workpiece. So that very high pressure gas, it expel whatever the molten material is there uh, at the hole. Okay, whatever this molten material is there, no? So that expel the molten material, okay, from your chamber. Okay, so whatever this recast layer, okay, whatever this molten material, whatever this re-deposit on your workpiece, no, so this that recast layer, it can be reduced by this chemical backing material. Okay, when that recast layer is going to produce, okay, because when a molten material, when it will deposit on your that machined surface, no, that recast layer uh, will be produced. So to reduce the recast layer, this chemical backing material is you okay, or due to the chemical backing material, that recast layer will be reduced. Okay, so this entire chamber, actually whatever the machine chamber is there, so that entire chamber, it is actually uh, full with, or made uh, made up of the vacuum to reduce the possible collision of the your electron beams, okay, with the air molecule. Okay, so please remember. Okay, so this is about the working principle of your electron beams. Okay, I think you got it. Okay, understood. Now let us go for the next one. In this slide you can see here. So here you can see there are different elements of electron beam machine systems. I have shown in this. Okay, different electron. So the most important and the first one element of this EBM process system is that electron beam gun. Okay, like laser gun. Here also electron beam gun is used. So electron beam gun. And the second element is power supply as usual. And the third one is the vacuum system. Okay, and that vacuum system and the machine chamber. So electron beam. Now I'm going to talk about the first one, that is EBM gun, electron beam gun. So it operates in the pulse mode. Okay, your electron beam gun, it operates in a pulse mode. So there are some biased electrodes are used. So by controlling this electrode, you can generate the electron beam. So pulse electron beam you can generate. Pulse electron beam you can generate. So it yeah, that electron beam gun uh, produce focus the electron beam on a predetermined location. So there is a actually superheated cathode is there. Okay, to generate the electron beam, you will know that. Okay, and it that may again one important point that filament sorry that cathode it is usually it is tungsten filament, okay, which is heated up with the very high temperature, or you can see uh, you can use a solid block of cathode, okay, which is heated by radiation of the uh, filament possible. Both things are possible. So because of this heating of this cathode that is tungsten filament, electrons are actually generated surrounding to your this cathode. Okay, so this electron clouds because of this these are uh, actually that are produced from the cathodes, and that means that they are these are the negative charges. And it is expelled because of the repulsion force of your cathode from the that will expel from your cathode, and it is attracted by the anode. Okay, by the anode. Okay, it is attracted by the why that is attracted by the cathode because it is opposite charge. And then it is passing through the magnetic lens as usual. We know that. So when it's passing through the magnetic lens, so a convergent beam pinpoint, okay, at a localized, okay, a location can be generated. Okay, that means due to the magnetic lens, uh, all the that scattered electron beams can be concentrated at a localized area. So this beam is actually pinpointed into the small location when it okay, and then it can be bombarded on your workpiece. So this is the working principle of all these things. Okay, as I have discussed. Then I'm going to talk about the this power supply. Power supply is around 150 kilowatt, sorry, kilovolt high voltage that power supply is used. Because of this high voltage electron beam gun generate the your electron gun means your that cathode filament. It generates the electron. So this electron beam machining gun is a powerful system. Okay, it is operate at a 12 kilovolt, sorry, kilowatt. So pulse energy as high as 150, 120 joule per pulse that power can be generated from this electron beam machining gun. So computer control of the process variable can be generated. So all these parameters are controlled by the computer. Okay. So due to that high power density, actually that high power density of your electron beam is required. Okay, to melt or to vaporize your workpiece metal. So that high power density is required for melting and vaporization of the metal, and it will give the high. Due to that, it gives the high metal removal also. Okay, and as a huge amount of energy by the collision of this electron are generated, so metal is machined mostly by the vaporization of this metal. Okay, please remember this one. So now the third one is a vacuum system and the machine chamber. Already I told this machine chamber is a vacuum. So as the beam actually travel through the machining, so it may collide with the air. Okay, with the air molecule. So that is why to avoid the collision of this electron beam with the electron with that collision with the electron with the air molecule. To avoid that, machining chamber is made vacuum. Okay, so pressure inside your machine chamber is maintained near about 10 to 10 to power 10 to 10 raised to minus 4 to 10 raised to minus 5 torque. Okay, so because of this vacuum, So there is no oxidation of this your tungsten filament. Otherwise, if it is not vacuum in the your mustard chamber. So whatever these oxygen molecules are there inside your air, it will oxide your tungsten filament, so which is heated up to a very high temperature. So there is a no collision of these electrons due to the vacuum and the air molecule. And so due to that, again, no loss of the energy of this electron because of this vacuum chamber. Okay, so this is the important importance of the vacuum. Okay, so these are the different elements. Now let us discuss the process parameter. Process parameter. You can see uh, uh, the simple question arises that what are the different process parameter of this electron beam machine? So this process parameters here I have listed that uh, beam current, pulse duration, then a lens current, then beam deflection signal. Okay, so these are the process parameters: beam current, pulse duration, duration of this pulse. As I told that electron beam machining system, this machining is going on by the pulse mode. Okay, not in the continuous mode. So that due to that beam current is important. Again, the pulse duration. That current to the lens magnet lens, and then deflection, that beam deflection deflecting signal. These are the parameters. So these are the four parameters, four important parameters for this electron beam machine. Now we'll discuss one by one. So this beam current. Okay, first is the beam current. So it may be it varies from beam current. It varies from 10 microampere, sorry, 100 microampere to 1 ampere. So this beam current actually governs the what is the energy per pulse. Okay, it governs the energy beam energy per pulse on your workpiece surface. Okay, if a higher value of this beam current, then that higher value of this beam current will generate the high beam energy per pulse, and it will generate the high material removal. Okay, please remember. So by changing this beam current, you can change the beam energy, or you can change the material remove rate on your workpiece surface. Okay, so this is a very important parameter, beam current of this laser beam. Now, second, pulse duration. So this duration of this pulse, it varies from 50 microsecond to 10 millisecond. So longer pulse duration will generate the wider and deeper holes. So if we put this pulse uh, on a for a long duration, for a long duration of the time on your workpiece surface, so obviously it will generate a wider shallow holes, but deeper holes. Okay, because it keeps on it is kept on your workpiece surface at a certain time for a longer period of time. So due to that only you will get the wider shallow holes, but deeper holes. So it would generate the wider and deeper holes, and again it affects the this pulse duration. Also it affects the heat affected zone on your workpiece surface. So because of this heating of this surrounding metal, it generates a higher heat affected zone. Okay, if this pulse duration is increased. Okay, so that is the effect. So due to that, this recast layer, the dimension of the recast layer in case of this laser beam machining is 25 micron, or around 25 micron. That recast layer will be generated. Okay, due to the higher pulse duration. Then a third process parameter is the uh, lens current. Okay, so now lens current. It determines the that working distance and the focus the beam size. So beam diameter, it determines the lens current. It determines the lens current. Determines the actually the lens current. It determines the beam diameter, and also it determines the working distance, and also it determines the what is the diameter of your beam. Okay, which is going to bombard on the workpiece surface. So be, this is about the lens current. Okay, now last one, the beam deflecting signals. Actually it affects the whole shape. Okay, whether the hole shape is a straight or the tapered hole. Okay, it is determined by the position of the focal point below the top surface of the workpiece. So this hole, uh, whether it will be straight or tapered, it depends on the this focal position, focal point of your beam, whether it is just the top side surface of your workpiece, or whether it is just below the workpiece. Okay. Here I want to mention is that for a non-circular hole beam, uh, for non-circular hole, your beam movement can be programmed. So other than a circular hole, this beam movement can be programmed. Okay. So these are the process parameters. Uh, Now I'm here. I will mention the formula about the material removal rate. Okay, how to calculate the material removal rate for this electron beam machine. Okay, so this is a this material removal rate is calculated by this formula. You can see. Okay, okay, material removal rate means what? Rate at which workpiece material is vaporized. Okay, eta into P divided by W. Okay, and where eta is the uh, cutting efficiency. Usually it is below 20%. And P is power, okay, joule per second. And W is the specific energy, joule per centimeter cube, okay, which is required to vaporize your workpiece. Okay, and by simplification of formula, you'll get okay. Uh, to calculate the specific energy, that W, here again the formula I have given, that CPS. Okay, that is where CP is the specific heat, TEM minus TI. Okay, so the Tm is the melting point temperature, Tm is the boiling temperature, boiling point temperature, then Hf and Hv, latent heat of fusion, latent heat of evaporation. Okay, so here Cp is assumed to be constant, although it varies with the temperature. But here to calculate the MRR, material removal rate, that Cp we have to assume to be constant, and that suffix one of the yes is given. Yes and EL are given. Actually, it indicates the solid and the liquid state respectively. Okay, so you should know the formula. So for that purpose, I have included this point. Okay, now the characteristics and application, these 2 points are remaining that we'll see in the next lecture. Okay, so I request all of you, please write down your roll number, okay, in the chat box. If you have written already, then no problem. No need to write one side. Okay, I hope you understood this electron beam machine. Again, at 1 o'clock, another my one more lecture is there. So that time we'll cover the remaining point, and we'll see the one two small videos related to the working principle of electron beam machine. Okay, I hope the attendance will increase at the time of that. Okay, next lecture. Okay, I know very few students are attending. Okay, those students who will attend the all lectures, or who having the attendance more than 70%, definitely it's a positive effect I'm going to give at the time of your ISA marks and the term of the, okay, definitely you will get the more than the 22 marks. Okay, please write your roll number. Okay, so all of you, thank you very much. You can do this meeting.